Okay. Um, so I want to welcome everybody back again today. And Peg, you introduced Kristen.
I Not much. You want to
Okay,
give her a little better introduction?
sure. So Kristen Metzger works with me at Rubin Observatory. She's our science communications writer, and she has graciously volunteered to help out today. So Kristen will be monitoring chat, dealing with questions, and also um, kind of keeping time for us to make sure we're on time. So thank you for understanding our tech issues yesterday. If you were one of those people who suffered through problems with connecting, and we appreciate your understanding and your graciousness for dealing with all of that. I wanted to begin today by going through some of the questions that you posted yesterday in your optional question form, dealing with some of that because that is a pretty important thing. So I'm going to stop sharing my screen. And I'd like to go to some of these questions that you asked. So there were quite a few questions yesterday about your how are answers getting saved, and uh, right now we have no way to save answers from students or you. Um, as I mentioned yesterday, these are first drafts of activities. And what we're doing first is building out the investigations, and later we're building out the infrastructure for supporting those investigations. So right now, for instance, we don't have a web page. We don't have the back-end infrastructure for saving data and accessing data. So what you have right now is just simply investigations. And if you wanted to save answers, my suggestion would be that you screen share or screenshot any data that you wanted to save a picture of, or that you write down the answers, because they will not persist. However, in the future, we will develop persistence for these. So even if, for instance, somebody wrote to me from Alabama yesterday and said, sorry, I dropped out halfway through when my school lost power. So I mean, even if you have like a power failure or a fire drill, there will be a way for your answers to be saved in the future, but we just don't have a way to do that right now. Second thing I wanted to mention to everybody is a number of you wrote to me yesterday and said you're interested in user testing. I did not reply to all of you individually. I will do that probably after this week's workshop, because as you might imagine, I'm getting quite a few emails every day right now as we're dealing with the workshop. But I did get your messages and I will reply to you. I wanted to thank all of you for your tremendous collaborative work yesterday. I was delighted to see that yesterday that so many of you were posting questions, and then somebody else in the group just jumps in with the answer. And that was great. So please keep it up and keep up your work in the breakout rooms, because I think that was very helpful to most of us yesterday. I wanted to also mention to you that we have posted a new video on the main page of the meeting, the page that precedes day one, by Margot Lopez. And Margot Lopez first volunteered to give us a talk on Rubin Observatory, but because we were limited to a 15-minute time slot, she said, why don't you just watch my video that I made about Rubin Observatory instead? I think it's about 38 minutes long. So we've posted it on the front page of the meeting page if you'd like to learn more about our telescope and data and all that will come. So I just wanted to let you know that that's a new link that was posted just this morning. Going through a couple more questions that you posted yesterday. Some of you had questions on the vein of how do you make sure students are trying to answer questions and not just clicking through answers? If they're not in a certain range, do you make them try again? Well, no, we don't. In the same way that if you do a pencil and paper activity, there's no reinforcement to say it's a wrong answer, do it again. However, there are some instances where you will see, and I think one of those is today, where if you don't click on something correctly, there will be a little message that pops up that says, try again. So even though we don't insist on correct answers for things like multiple choice or open-ended questions, we do have some technology prompts built in if you're not quite handling the data in the correct way. That's not true everywhere. It's just true in some instances. You know, there were a number of you that also wrote about, am I going to get feedback if my answer is wrong? And again, most of the time, no, but some of the times, yes. And then there were a number of questions about how do students submit information about their answers? And again, we don't have any plan for that right now, but we are going to be building that out in the future. On day 5, we're going to ask you a number of questions about what is it that you need to be able to evaluate student work. So it might be that you have some very specific needs to interface these investigations with your content management systems. It might be that you would be satisfied with a printout of an answer sheet or a PDF that gets submitted to you. So we are asking those questions of you. It's just not today, but we're going to take that feedback and we're going to consider what it is we need to design for the future, keeping in mind that we're a very small program and we're not going to be able to do anything incredibly flashy and fancy, but we are certainly going to find a way to get answers delivered to you as the instructor. I also would like to address a question that came up that says, this activity asks questions about what is the highest value in the class. It implies light curves will change. Is this because the program will pull random ones from a bank? We have designed all of our investigations to be interactive with peers. Now, I know that doesn't always work in a totally virtual environment, but when we wrote these investigations, we didn't know that the whole world would become virtual all of a sudden. So you'll have to deal with some of those questions occasionally where, you know, you're supposed to discuss with the class. One way you could do that is set up a chat in your course management system. You could totally skip it or just have students answer individually. But yes, we are going to have different data. So in some investigations for testing purposes, everybody gets the same data. So yesterday, you all got the same supernova data, but in the future, we're going to have such a vast data set to draw from. You know, many people describe it as drinking from a fire hose, that everybody will have unique data. Every person will have some ownership, or every group will have some ownership over the data they see. And that's where that interaction value comes in. In some cases this week, you will see that depending on who you're working with, if you pulled up 2 instances of an investigation, you'll get a different data set. So it's not always the case with these test investigations that everybody gets the same data. Even if you do it twice, you may find out that the second time you do it, you have a different data set. So right now, our data sets are very small and limited for testing purposes, but in the future, they're going to be very large, larger than you need. And then there's also a number of questions that we'll probably have a discussion about later, about how do you get to the actual data? How do you make use of it? If you just want the data, and you don't want any tools, and you don't want this investigation, how could you do that? Well, there is a scientific interface, and if you are a US educator, you can get into that scientific interface because you have total data rights to do that. If you're in other countries, it gets a little stickier, and we can talk about that individually in terms of your needs. But certainly, if you're accessing the data from our EPO department, from our education investigations, there is no restriction on who could use it. You could use it around the world. So I'm going to stop right here because those were the main questions I wanted to address today. And I just wanted to ask if anyone has questions that you would like to ask right now.
Artis, we got a question in the chat about whether it'll be possible to use QR codes for sharing the investigations and the presentations.
Well, that's an interesting question. I'm not exactly sure how that works. I'm not sure who said it, and maybe you could give us a little bit more detail about what you're thinking.
Yeah, let me, Padma, if you could request to unmute.
Okay, can you hear me?
Yes.
Yes.
Oh, okay. You know, I did a lot of outreach and amateur astronomers collaborations for Rosetta mission. And one of the things I did find was if I did a poster, many of the amateurs obviously couldn't attend the meeting. So I would then make a QR code that I would display on the poster, and they would get all the information that I was talking to other scientists about. And that really worked very, very nicely for me. So I was wondering, since you have a small team, you have so much data, practice data, but you also have great presentations as well as wonderful data that I'm hoping is going to be coming down shortly. Is there a way to either encapsulate the data sets and or the meetings so that people who always can't, even though you have access to a PDF file, etc., the QR code encapsulates all the information, and apart from the audio part of it, but you can create it for many social media also, so that I think it is extremely valuable to investigate that. And if that is something you want to do, I can help you with it. But if that's really something you want to do, you want to start from the start so it's consistent. And then there's a QR code associated with each product that somebody, even if they don't have the time, can at least take a picture of the QR code and come back and look at it later. And so with a small team, I think that's a very effective solution. It's a little bit of investment of time and money, but it's worth it.
Okay, thank you. That's an interesting idea. Anybody else?
Artis, we have one more question that is, where do we find the data?
Right now you don't. Well, for several reasons, right? Our telescope isn't built yet all the way, so it's not producing data. And that's probably not going to happen until, what, Kristen, 2024? Is that what you imagine? Our first
data? That's what I think.
Now, we in the education department will get some preliminary data before the official data release, and we'll be moving those into our investigations as we are able to. So gradually what we'll do is we'll replace the proxy data that we have now with actual Rubin Observatory data. But for right now, there is no data to get, and we will develop some sort of procedure in the future, but I don't think anybody can tell you what that is right now.
And we'll do one more question here, and then I think, Artis, you need to move on to the next subject. But
Yes.
The question is, I understand the apps are in the development process, but will we be able to use some of the features in the fall with our students?
Right, Maria. So you can, as long as you use it in a testing situation. So I spoke with some of you about this yesterday, but because we are a construction project, we are constrained by the National Science Foundation rules for construction projects. And what we are not allowed to do is officially do outreach. So we can't just disseminate these investigations right now. They're not classroom ready, as you discovered yesterday, and you'll see this through the week. But you can try them with your students if you agree to do a user test. What that means is that you could use our investigation, set it up with me in advance so we make sure that the link is working for you on the day that you want to use it. And then I will send an evaluation form like the ones you filled out yesterday. It's about a 5-minute evaluation form, and ask that all of your students do that as a condition of using the particular investigation you'd like to use. And that's all we require. We do not collect any information such as a student ID or an email address or a name. So everything we do in terms of testing is totally confidential and anonymous. Okay, well, these are good questions, and thank you. So the next thing we're going to do before our guest speaker today is I'm going to talk to you a little bit about hooks and phenomena. Now, some of you might be familiar with these words, and others of you might not know what I'm talking about. So I'd like to preface this a little bit by explaining what do I mean by a hook. So a hook in the simplest sense is some sort of engagement activity. It could be a short discussion that you have by looking at a picture. It could be looking at a data visualization. And it's kind of like a warm-up, if you will. It's a way to get your students engaged in the activity. Now, some of you use those and some of you don't. If you are teaching in the NGSS world, you know that same idea as a phenomenon, but there is a little bit more detail involved in a phenomenon, and there's a little bit more deeper meaning in it rather than just simply an engagement. And what I would like to do, I'm going to attempt to do this right now, is to take you to the expanding universe phenomenon and share my screen and talk to you a little bit about what we're planning on doing and what we would like to know from you in terms of input. So let's see. Okay, does everybody see something that says phenomenon on it? Yes? Okay. So this is a document that you have a link to under your resources. You have a similar document called Expanding Universe Hook. So depending on what world you might live in, the NGSS world or not, yeah, these documents are very, very similar except at the very end. So we're going to take you through an example of a phenomenon that we created, a first draft of it, on the Hoberman sphere. Today we're looking at an app called the Expanding Universe. And so we were trying to think about, well, what would be an engagement piece for the Expanding Universe? So what we have here as a document, and we're envisioning this is the kind of support level that we would provide to you, is just a short introduction of the document. And in this case, we made a little video, a little homebrew video to show. And so we have a script here of questions that you could ask your class as they view that video. But we did not put these questions on the video because we thought you might have different words, or you might want to skip some of these questions or add some of them on your own. So we just gave you some suggestions about what you could say. At the end of this, we have something called storyline integration. Now, if you are an NGSS educator, you're very familiar with storylines. This is the sequence of lessons that you build out to try to make sense of a problem that you're trying to solve, or something that you're trying to figure out. And so what we've done here is we've given you some sample storylines that this phenomenon might drop into about, you know, how do you measure distances in space, or how do you know the universe is expanding, etc. If instead you looked at the Hook document, you would see the same thing, except where it says storyline integration here, it would say learning sequences. And it would have some ideas about, in your syllabus, where would you drop this in if you wanted to use it. What you will only see on the phenomenon document is this landing discussion. So one of the pieces of NGSS is not only do you use the phenomenon as an engagement piece, but you return to it at the end after you've gone through the investigation, after you've tried to make sense of something, and you do a follow-up. So many of you are familiar with what's called launch, learn, land. It's kind of a technique where you start with something, you try to make sense of it, and then you revisit it. And so what we've done here is we provided some questions that you could go back and watch this video again, or talk about this video again, and say, you know, how does this match up based on what you know now? Is this a good model? What are some flaws with this model, etc. So this is kind of the support document we've created for teachers. And now what I'd like to do is just walk you through how this might work. Our Hoberman sphere video is found at this link. Now, before I go on, do you see a video on your screen? Okay, good. With Zoom, I'm never quite sure what screen I'm really sharing. So I'm going to attempt to walk you through some questions I might say while I play this video. And at different points, I'm going to stop it just to kind of give you a pause. You do not have to respond to these questions, but I just want you to see how this might work. Today, we are going to be investigating a model for the universe that expands called a Hoberman sphere. The purple grid structure of this model represents the space-time of the universe, and the green diamonds represent galaxies that are embedded in the space-time. In this model, the space-time of the universe and the galaxies make up the entire universe. There's nothing inside the sphere nor outside the sphere that is part of the universe. This model shows the universe at an early time when it was smaller than it is now. As time goes forward, how is the size of the universe and the distance between galaxies changing? This represents the universe as it is today. Now let's watch this again. Over time, do all galaxies appear to be moving away from one another or toward one another? Does this show the universe has been expanding or contracting? There are 3 galaxies in this view that are marked by colored circles: cyan, orange, and yellow. Let's imagine the cyan colored galaxy is the Milky Way galaxy, and we will watch as 2 galaxies move away from the Milky Way galaxy while the universe expands from an early time until now. Well, as you watch this, which galaxy appears to move away from the Milky Way by the greater amount? The near orange galaxy or the far yellow galaxy? Now, since the motion of these galaxies is happening over the same amount of time, which of the galaxies would an observer in the Milky Way galaxy say is moving the fastest? The closer galaxy or the farther galaxy? Let's watch this one more time. Are the galaxies moving to different positions on the grid, or are they staying in the same position as space-time expands? Now let's imagine that we live in the orange galaxy, which is close to the Milky Way galaxy. Do you think the universe will expand in the same way as it was when you were located in the Milky Way? Which galaxy would you predict will move the farther away from you and faster while you are located in the orange galaxy, the Milky Way or the yellow galaxy? You've now viewed expansion from two different galaxies in the universe. What do your observations suggest about where or if there is a center to the universe? We're now going to watch 3 videos that demonstrate 3 different ways that the universe might be expanding. What was different about the expansion rate in these 3 videos? Which of these 3 videos do you think best represents how our universe has been expanding since the time of the Big Bang until now? Now let's imagine you could run time backward with this model and watch how the universe changes. Based on your observation for time running backward, does this model support the Big Bang theory? If it does, in what ways? Okay, we have just about 1 more minute left until our guest speaker, but I wanted to just wrap up by telling you that our plan is to design some sort of hook or phenomenon for each investigation, which is an option for you. You don't have to use it, but you could use it, perhaps in advance of the investigation or the day before if you want to. Most of our plans do not involve a video. But when we sat down and thought about if we're going to develop one phenomenon for you, what is it going to be? What would be the most common one that you would use out of the 5 we show you this week? It was expanding universe. And it's awfully hard to show expansion with a static image. So this is probably the only video we're going to develop. But tonight we're going to ask you on the evaluation forms to give us some feedback about what you think of these, if you would use them, how you would change them, etc. So thank you. Peg or Kristen, is Keith with us? Yes, okay. So I'm happy and pleased to introduce our guest speaker for today, who is Keith Bechtol. Keith works at the University of Wisconsin-Madison, and he's also very deeply involved in studying the part of the universe that we can't see, the things that are not made of atoms. And I'm very pleased that Keith agreed to speak with us. I think Keith is an excellent speaker. He also is a teacher like you, and so certainly understands the needs of the classroom. So with no further ado, I'm going to let Keith take it away. And thank you, Keith.
Great. Thank you for the introduction, Artis. Can people see this presentation screen? That looks good. Okay. So I understand it's probably a broad range in the audience today. So my goals are to give some scientific context for understanding the Hubble diagram, which is going to be the activity that's shown later, and why this is interesting, and how, just very briefly, how the Rubin Observatory can contribute to that effort. So let's begin. So we live in an expanding universe, and this is a visualization to try to one way of seeing what an expanding universe might look like. So each of these points is representing the location of a galaxy. The colors are just to identify the different galaxies. And we can imagine that we live in one of these galaxies, for example, this blue circle highlighting the red galaxy here. And what we can imagine is that if the universe is expanding, then we can take a snapshot at a different time in the history of the universe, when the universe was a little bit smaller. So what I've overlaid here is basically the same set of galaxies for when the universe was just a few percent smaller than it is today. And what we'll do is it will basically shift how this set of galaxies would look if we were to shift the perspective to different galaxies. So first thing you'll notice is that this differential between the locations of the galaxies, as you get further away from the current galaxy marked with the blue circle, that differential is increasing, meaning that the galaxies appear to be moving away faster. But if we imagine shifting the perspective to other galaxies, we see that in this expanding universe, effectively all the galaxies would have the same impression, that it looks like the galaxies are moving away from them, and that as you look at galaxies that are further away, they appear to be receding at a faster rate. So this is one way to visualize what we mean by an expanding universe, that the typical distances between galaxies is growing with time. And so if we were to try to create some mathematical relationship between the distances to nearby galaxies or faraway galaxies, some indication of their distance, and then the apparent recession speed, what we would predict in an expanding universe is that there'd be this linear relationship where the galaxies that are further away from us appear to be moving away at a faster rate. And that's because the overall scale of the universe is increasing with time. So this is what we would predict theoretically. And oops, if I go forward, this was actually observed experimentally. The first Hubble diagram was made around 1929. This is basically Hubble combining the spectroscopic information collected by Bechtol, looking at nearby galaxies and their apparent motion away from us as measured by looking at their spectral lines, and then the period luminosity relationship from Henrietta Leavitt that could calibrate the luminosities of Cepheid stars and those galaxies and use that to estimate the distance. So it turned out that the initial estimate of the expansion rate estimated by Hubble was off by almost a factor of 10. The modern measured value for the expansion rate today, basically at right now in the history of the universe, it's about 70 kilometers per second per megaparsec. And a way to think about this is that a galaxy that is 1 megaparsec away, about 300 million light years away, this is approximately the distance to the nearest large galaxy, to the Milky Way Andromeda, would appear to be moving away at about 70 kilometers per second. And so this is sort of the statistical relationship that we would expect as we look at galaxies that are further away. They would appear to be moving away faster at this linear rate. Now, there's actually two different contributions to an apparent wavelength shift. So this would be, for example, the redshift, how quickly a galaxy appears to be moving away based on its shifted spectral lines, for example. So one contribution comes from the relativistic Doppler effect. And this arises from special relativity, and it's actually something that's used to measure, for example, the speeds of a tennis ball or a baseball in sports. The relativistic Doppler effect can be used to tell us the relative velocity between an emitter and an observer. There's a second effect which contributes to an apparent wavelength shift, which is the cosmological redshift. And this is related to the relative size of the universe when the light was emitted and when it was received. And in fact, if you measure this wavelength shift, you can tell what the size of the universe was when the light was emitted. It turns out that the cosmological redshift is the dominant effect when we look at galaxies that are further away than, say, 100 million light years. So basically, once we stop looking beyond our immediate neighborhood of nearby galaxies, this cosmological redshift is the larger effect. And this is how we interpret the overall recession of all the galaxies that we see in the observable universe. You could imagine trying to explain that effect with the relativistic Doppler effect, but actually would be quite a contrived situation because you'd have to imagine that all the galaxies somehow coordinated to move away at the exact right velocity. And so the cosmological redshift is a much more natural answer. And this is evidence for the expanding universe. So one way that we can try to understand the expansion history of the universe is to look for supernova explosions. And so I think probably Federica talked about this a bit yesterday. So the idea is that as you're observing the night sky, you return to the same patch of sky many times. And what you might find is that at some later time, you return to a given galaxy and you see that there's a bright flash of light, a supernova. And there's a certain class of supernova, type 1a supernovae, that are explosions of known intrinsic luminosity. So in particular, the peak brightness of this type of supernova is about 10 to the 36 watts. If you know the intrinsic luminosity of this supernova, you can take the observed flux at the Earth, and you can use that to estimate a distance. And if you know the distance, then you can compute the light travel time from when the supernova exploded. So basically, if you know that light is traveling at about 300,000 kilometers per second, you can try to estimate how long it took for the light from that distant supernova to reach you. The second observable that you have is the redshift, basically the shifting of the spectral lines, for example. And in an expanding universe, that redshift tells you the size of the universe when the supernova exploded. So effectively, from each one of these supernovae, you get basically a time, an age of the universe, and a relative size of the universe. So if we go back to our Hubble diagram, we can imagine sort of relabeling these axes such that the distance axis is now telling you about the age of the universe, and the apparent recession speed, or the redshift, is telling you the size of the universe. And in fact, if you look at supernova over a range of different distances, this allows you to trace out the expansion history of the universe. So a couple interesting comments here. One is that, the slope of this relation tells us the matter energy density of the universe. This arises from general relativity. It turns out that the current value is equivalent to about 6 protons per cubic meter in terms of the energy density. So that's one interesting reason to measure this expansion rate. A second motivation is that the inverse of the slope, which has units of time, actually tells us the approximate age of the universe. And so if you take this value of 70 kilometers per second per megaparsec, and you basically trace when would the universe have been at the point of the Big Bang, you would estimate that the age of the universe is about 14 billion years. And that's actually quite close to the more precise value. The other interesting thing is that it turns out that the rate of the expansion has actually changed throughout cosmic history. And this starts really getting at all the interesting physics that we can get out of this relationship. So the next couple slides are going to show a series of plots, getting a little bit more quantitative and try to get at really sort of the physics motivation for why we would want to understand the expanding universe in detail. So this particular plot on the horizontal axis is showing the size of the universe, and this is on a logarithmic scale. So on the far right-hand side of this plot, this would be the size of the universe today. And then the far left-hand side of the plot would be when the universe was 10,000 times smaller than it is today. And you can see that because we're in an expanding universe, I've marked out a couple different key epochs, right? An age of around 6 giga-years ago, 6 billion years ago. And then at the time of the cosmic microwave background, this was when the age of the universe was about 400,000 years old. The vertical axis here is the expansion rate. So this is telling us how quickly the universe was growing. And the interesting thing here is that we see these 3 different regimes where there's been a slope change. And we can actually associate these different epochs of the universe when the universe was expanding at different rates is corresponding to 3 different periods when the dominant form of matter and energy in the universe basically came from different components. And so we have a radiation-dominated period, a matter-dominated period when the galaxies were growing, and then the most recent period where dark energy has taken over. So it turns out that these three components, the reason why we have these different epochs in the universe is that the density of matter and energy in these three different components, it changes for each one of the different components. So basically they have different rates in which the density is reduced as the universe expands. So in particular, you'll see that the radiation drops off most quickly. And this is why the radiation becomes, a subdominant factor in controlling the expansion history of the universe after only a few 100,000 years. Then there's this long period where the matter density is falling off, and this is falling off as you expect with the volume. The really curious component here is the dark energy. And here you see, as the universe expands, the density in dark energy just stays the same. Right, so this is very unusual. We don't know of any other substance that behaves this way. Another way of thinking about this is that this dark energy just has a constant equivalent density, and the energy density is equivalent to about 4 protons per cubic meter in our universe. That's the approximate measured value. So it turns out that if you were to look at the fraction of the total energy density in these three different components, it's actually changing quite a bit over the history of the universe. Again, we have this period where radiation was dominant in the early universe, this long period, many billions of years where the matter density was the largest matter energy component. And then most recently, we have the dark energy taking over. So the amazing thing about all of this is that all the observations we have from the present day, ranging all the way to about 1 second after the Big Bang, can be explained by a relatively simple cosmological model. And I mean simple in the sense that it has very precise predictions and is only controlled by a few free parameters that we can measure experimentally. The thing is that this model, though, it has 5 distinct lines of evidence for new physics: dark matter, dark energy, massive neutrinos, inflation, and the matter-antimatter asymmetry. And so in some ways, I liken the period that we have now to maybe around the period of around 1900 in the history of physics, where we had made a tremendous amount of progress and in many ways had a model that was very successful in explaining diverse phenomena. At the same time, there was this revolution on the horizon that fundamentally changed our understanding of matter, energy, and space and time. And in the year 1900, that revolution was going to come in the form of quantum mechanics and of general relativity. And in the next 10 years or maybe longer, maybe these 5 lines of evidence will point us to some new revolution in physics that again makes us realize that maybe we weren't even asking the right questions. So this is all significantly compelling that there are hundreds of scientists around the world that are planning to use data from the Rubin Observatory to try to measure this expansion history of the universe and then to learn about what new physics that might be telling us. And so this is a picture from a recent collaboration meeting of the Dark Energy Science Collaboration, which is one of the 8 science collaborations that are planning to use Rubin data. And so there's actually many different ways of trying to study the expansion history. Supernova continue to be one of the really exciting techniques that we use. And so the reason why this is a challenge experimentally is that these type 1a supernova occur about once per century in a large galaxy like the Milky Way. And so you'd have to wait a long time if you're only looking at one galaxy. But the Rubin Observatory's Legacy Survey of Space and Time, LSST, we will be monitoring something like 10 billion galaxies over a period of 10 years. And that means that we'll be able to get a sample of something like 1 million type 1a supernova. They're actually spanning billions of years of cosmic time. And so we can really trace out this expansion of the universe in exquisite detail at about the 1% level. And we're hoping that that will give us this new insight into the laws of physics. So let me stop here. I've posted just a couple frequently asked questions about the expanding universe, but I'll pause here and see if there's any questions I can help answer.
Keith, in the chat box, we had a question, is how do we know that all type 1a supernovae have the same brightness?
So actually we know that they do not have all the same brightness, but rather we can look at information about the time evolution, basically how quickly the supernova gets bright and how quickly it fades away again, in order to calibrate the luminosity of the type 1a supernova. And even then we know that with this calibration, there is still a scatter. Basically, if you take any given supernova, we can only estimate its luminosity at about the 10% level right now. And so that is one reason why the Rubin Observatory is excited, you know, why we've sort of designed it in a way to collect many supernovae, because we have to essentially know that there's a statistical uncertainty, but if we look at something like 1 million supernova, we'll be able to calculate on average, you know, what was the distance of supernova at a given time in the universe. And so it really becomes a statistical measurement because we know that one supernova isn't going to be enough.
Okay, we have actually quite a few questions coming through. Could you speak a little to the current discrepancies between, and I apologize, I'm a writer, it's H_0 values?
Yes, so this has actually become one of the hot topics in cosmology research today, is that, so I think it'll actually help if we go back to, which plot, sorry. If we go back to this plot, so there's actually multiple different ways of measuring the expansion history of the universe. I focused on the type 1a supernova just for the sake of clarity, to sort of focus on one particular probe that was associated with the lesson today. But there's multiple different ways of measuring the expansion history of the universe. And it's a very interesting question to look at these different methods and see if they give a consistent answer. Because if the different ways of measuring the expansion history of the universe give us different answers, then it could tell us that maybe the whole paradigm that we've been working in has some kind of flaw or needs some sort of adjustment, and that would give us new insight. And so, in particular, the tension or apparent tension that seems to exist in the current measurements is that there are methods that look at the expansion history of the universe basically by looking at galaxies in the relatively low redshift or near time, you know, sort of in the recent past, basically trying to directly measure what is the expansion rate of the universe today, right? So it's sort of at relatively near times. But then there are also a set of methods that try to look at the very early history of the universe, in particular looking at the cosmic microwave background or the particular pattern of density perturbations that were laid down at the time of the cosmic microwave background and that basically control how galaxies are distributed in the universe today. And what we can do is that we can look at the data from the cosmic microwave background from this very, very early period of the universe and basically forward predict what we would expect the expansion rate of the history to be today. And it turns out that those two different numbers, basically what you would predict from the time of the cosmic microwave background from the early universe and what we measure today, they differ by, you know, something on the order of 5 to 6%, something like this. But the quoted precision of these measurements is sort of at the 1 to 2% level. And so it's an indicator that maybe there's something different in the physics of the early universe and the late time universe that we don't understand. at the same time, it could be potentially an indicator that there's some sort of way that we've done our measurements, some way that we've calibrated our data that could be slightly off. Because again, we're trying to make these measurements at the 1% level. And so that's one reason why scientists are so excited about the Rubin Observatory, is because it potentially gives us another set of handles to try to understand that discrepancy, or at least apparent discrepancy.
Thanks, Keith. Okay, so Ian Gray asks, so how do you feel about the flat versus curved debate right now?
Oh, I would say that the overwhelming evidence is for a universe that is quite flat. That's not to say that it couldn't have some deviations from flatness, but those deviations would have to be at the level of about the part per thousand or less. And in particular, there's also sort of good theoretical reasons to think that the universe is very close to flat, because as the universe has been expanding over billions of years, any deviations from flatness grow dramatically. And so we basically tried to understand this in terms of setting the initial conditions of the universe in a way that almost guarantees that the universe is very close to flat. And so this is part of the inflation, this evidence of new physics that I mentioned. And so I would say that it's definitely a topic that we will continue to investigate and try to make more precise measurements. But as of right now, there's no, I wouldn't say there's any, within the precision of all experiments that exist today, there's no indications that the universe has a measurable curvature.
All right, we've got time for one, maybe two more. So do you expect the LSST data to resolve the Hubble tension, or might there be some kind of systematic error?
I think that the Rubin data will be one piece, in the sense that there are multiple different ways of measuring the expansion history, this Hubble constant, right? That's the expansion rate of the universe today. But ultimately, it is probably going to require other instruments as well, in part because you really want to have these measurements directly from the early universe, not only, so basically if you look at a galaxy survey like Rubin, you sort of get the most direct measurements in the sort of in the past, say 10 billion years or so, but we would also really like to have these measurements from the early universe. Rubin can get at that early universe information in an indirect way by looking at the baryon acoustic oscillations, which is this pattern of how galaxies were distributed, how matter was distributed at the time of the cosmic microwave background. So I think Rubin is a really important part of the whole story, but it's gonna take other observatories as well.
All right, I'm gonna do one more and then we need to move on because we need to give everyone a little time for a break. But the question is there a way to see how the universe looks right at this present moment, or can we only ever see the past?
We can only see the past. And this is because light travels at a speed of about 186,000 miles per second, or 300,000 kilometers per second. So when we look at the nearest stars, we're seeing them as they were a few years ago. When we look at the nearest galaxies, we're seeing them as they were, say, 1 million years ago. And in some ways, this is actually a beautiful, amazing thing, like a gift that the universe has given us, that when we look far away, we also look back in time, right? It gives us this opportunity. It's almost like being archaeologists, right? That we can see how the universe has changed. And so I'm actually like super delighted and grateful that our universe works out this way, that we can see the whole history. That's one of the amazing things that we can do.
All right. Well, thanks so much, Keith. Artist, do you want to step back in and let people know what's happening next?
Sure. Yeah, and I add my thanks to Kristen's, Keith, an amazing talk, and many of us are really, really excited and looking forward to these talks during the week, and they're complementing each other beautifully so far. So thank you, Keith, for your time. And I know you have to step back into your other meeting, but we appreciate the time you could give us today.
Thanks a lot. Have fun with the activity. I'll share the slides with artists so that they can be posted.
Right, thank you. We're going to take a break in just a moment, but I wanted to let everybody know, just a reminder that I posted in the homework last night, that you're going to need some pencil and paper when you come back, when you go into your breakout rooms. So what we're going to do is we're going to take a 5-minute break. My computer says 11:57, so let's try to come back at 02 after the hour at the latest. I'm going to speak to everybody for about 1 minute or less, and then we're going to put you into breakout rooms. So we'll see you back then. Thank you.